All right, we're back with oxidation state shortcuts. So this is probably what you're going to do because nobody wants to spend the extra time to prove it by drawing a Lewis structure and then spending extra time circling and labeling bullies from, wimps, so to speak. So what's nice about this shortcut is we're just using a lot of rules that we've already used throughout the semester. In rule number 1, they say elements in their natural state are always 0. So that should be nothing new. We learned that back in week 1. If your protons equal your electrons, that means no charge, right? You have as much positive as you have negative. You're not sharing with anybody because you're still in your elemental state, whether that's chlorine 2 or bromine 2 or nitrogen 2 or oxygen 2 or sulfur 8 or P4 phosphorus, all of those in their elemental state going to have no charge because they're not sharing with anybody other than themselves. In the next rule, we see that oxygen is a negative 2. Well, that's because it's probably never going to see a fluorine that's going to change its mind, and rarely does it see itself where it has to share in the sense of like peroxide to get a negative 1. So when you see oxygen, you can almost guarantee that it's going to be a negative 2 like we've always known it to be based on its distance from the noble gases. Hydrogen going to be a positive 1 just like the group 1 metals below it. So same family, same charge, even though it's not an alkali metal, it does behave like one. So group 1 and hydrogen be a plus 1 pretty much every time you see it. Group 2 a plus 2, no surprise there. If you're by yourself, if you're monoatomic and you're not sharing with anybody, your charge is your oxidation state. So let's say if sulfur is by itself at negative 2, then negative 2 is its oxidation state. That's another kind of no-duh. The sum of your oxidation states should add up to your overall charge, and that's the most important feature of this chapter. If you have a molecule like water, the charges of 2 hydrogens and the charges of oxygen should equal 0 when you're done. So 2 positive 1s and a negative 2 make a 0, and that's exactly what we're after. The sum should equal all the pieces. And then the last one is halogens are usually negative 1. The problem with that is except with oxygen. If those are with oxygen, they're going to get bullied, and they're not going to get what they want. So a lot of those hypochlorites, chlorides, chlorates, perchlorates are going to be bullied all over the place as you add more oxygens. So if you see a halogen when it's a bully, it's a negative 1 because it's going to get what it wants. But if it's not the bully, we have to watch out for that. So most of these rules, again, nothing new. They're just reminding you of the most important features of our earlier chapters. So as you look at the oxidation state of oxygen and water, we kind of did that just a moment ago. We have 2 H's and an O. So 2 H's and an O. And when we do that, we have to remember that based on our rules, hydrogen is a plus 1. And there's 2 of them. So if there's plus 1s and there's 2 of them, that means it's a plus 2 total. And then oxygen is a negative 2 total. Algebraically, we could write it as 2 H's plus oxygen equals 0. I'll put a slash to 0 to remind you it's not oxygen, it's oxygen is O. But as we plug this in, it's saying 2 positive 1s by rule plus a negative 2 by rule equals 0. And once you cancel like terms, this is a plus 2 plus a minus 2. And sure enough, 0 does equal 0. And that should be no huge surprise. But if we do hydroxide, hydroxide would be like O plus H equals negative 1. So if oxygen by rule is negative 2, we're adding plus 1. That should be a negative 1. And when you subtract those two numbers, you do get negative 1 equals negative 1, and that's what we want. So anytime you have a charge, notice you equal the charge in that kind of math problem. And we'll practice this in lab quite a bit. Water molecules are neutral, and notice because they're neutral, we say they're neutral in that kind of algebra problem. What's nice about both of these problems is whether you think about it in your head on how it needs to split apart and how it needs to equal, that's fine. Or if you have to use the entire algebraic process to solve for it, that's fine too. And even if you want to check your work and draw the Lewis structures for these and prove it based on electronegativities, that's also fine. But what's most important is, even if you have choices in the homework, you should be able to look at those choices and think, do all my charges add up? That was one of our rules at the bottom, I think number 6. So as we look at oxidation states, we need to make sure that they add up. And if they add up to 0, that's exactly what we want. That was rule number 7 of our list previous to it. So let's try another one. We have CHBr3. So algebraically, if we want to write this out, we could just say that there's one of these, there's one of these, and there's 3 of these. So carbon plus hydrogen plus 3 bromines all equals neutral compound 0. Carbon did not have a rule. So carbon is like X, so we're just going to rewrite it. Hydrogen did have a rule. Hydrogen it's a +1 when you find it in a compound. And bromine's rule, the halogen rule at the very bottom, was that it was a -1 as long as it's the biggest bully, and its electronegativity of 2.8 is much more than that of hydrogen at 2.1 and carbon of 2.5. So because it's the biggest bully, it's going to get that -1 charge that it's always wanted to be like a noble gas, and all of that equals neutral compound 0. So next thing we're going to do is combine like terms. So here we have this -3 and this +1. A -3 and a +1 is going to make a -2. And carbon is still there, and it still equals 0. In order to get rid of a -2, we're going to have to add 2 to both sides. When you add 2 to this side, the 2's cancel. And then we see that carbon, for the first time ever, is a +2 charge, which is not what it wants. But when you have 3 bullies, you get what you get. Should be able to check our work. If we have a formula of CHBr3, collectively this is a -3, this is a +1, and now we know that this is a +2. Notice together that makes +3 versus -3, and that makes 0, and that's exactly what we want. So you should always be able to check your work in these kinds of problems. So carbon +2 for the first time. So the reality of oxidation states for nonmetals is you're going to be anything between the noble gases. Sure, when conditions are perfect, you're going to get what you want. But the reality is most of the time, conditions are probably not going to be perfect. And you're probably going to get what's left over. And that's what's happening for carbon here. There's too many bromines, it's going to get the leftovers. Let's try this one here. This one should bring back some painful memories. Notice this is double. Wrong marker. Double. So that's 2N, and it has 2 O's. So this would be a carboxylic acid or an ester formula. But most importantly for this chapter, what's important is we do see that there's 2 carbons plus 4 hydrogens plus 2 more oxygens, all equals a neutral compound 0 overall charge. So again, carbon does not have a rule. If it doesn't have a rule, that means we have to solve for everybody else that does. So 2 carbons plus 4 hydrogens plus 2 oxygens. By rule, hydrogen's a +1. By rule, oxygen's a -2. That's from our list earlier. Here we have a +4. Here we have a -4, and those cancel. So we have 2 carbons equals a total of 0. Divide by 2 to get those 2's to go away. What you do to one side, you do to the other. That still stays carbon equals 0 by itself. So here, because we have so many bullies and so few hydrogens to give electrons back, carbon didn't go anywhere. And that's because the electrons that hydrogen did give to carbon were the same number as those taken by oxygen. So in the end, we look like elemental carbon and not anything else. So carbon is right where it is on the periodic table. It couldn't move forward, couldn't become negative because oxygen was bullying it, couldn't become positive either. So hydrogens would have given electrons to carbon, and they probably did, but because carbon was getting electrons taken from it by oxygen, it ended up being a zero gain in the end. So in a separate video, we're going to show you that everything we just did is part of a larger process to determine who's oxidized and who's reduced. So the ability to look at oxidation states and figure out where you start and where you end in a reaction is really what we want to get you to in this chapter. Everything we've done in the previous two videos is to get you ready for oxidation and reduction reactions. So we'll catch you in a separate video for that.